Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the previous classes, we are going through several problems in the carbocation, the carbanion, the carbene chemistry, and also in the last class I talked about some problem from the Grignard reagent and organolithium. In the today's class, I am going to talk about some more problem from the organocopper and organozinc chemistry. So let's start with the problem. The first problem is about the organocopper chemistry here. You can see there is alpha beta unsaturated carbonyl compounds and you are treating with a Grignard and a copper chloride. Now if you treat with just simple phenyl magnesium bromide in this alpha beta unsaturated carbonyl compound, what is going to happen? Your Grignard is a harder reagent, so it is going to directly go for a 1,2 addition with the. So if you have a phenyl magnesium bromide, it will go for a 1,2 addition and you end up generating a OMGBr pH, which once you protonate to generate the corresponding tertiary alcohol. But here this cannot be your product, because you have used a copper chloride with the phenyl magnesium bromide. So something else is going to happen. What is happening here? Once you have a copper chloride and once you treat with a phenyl magnesium bromide, what is happening here? You are generating copper phenyl organocopper species and you will generating a magnesium BrCl. Now once this is treated with one more equivalent of phenyl magnesium bromide, it is going to generate the corresponding cuprate. Okay. Now once this cuprate is going to react, again this corresponding cuprates are the softer reagent, that is not a harder reagent like corresponding Grignard or the lithium. So this is going to react with the alpha beta unsaturated carbonyl compound. Again you can see this OMG, the MgBr going to be activate, generate some sort of a delta plus character on that, and then copper is going to this piece is going to. So first there is a formation of a pi complex formation happen. Then from there is a two different pathway going to happen. One could be a oxocupration, one could be a carbocupration. So here you can see there is a copper and a phenyl here. Okay. Or there is a possibility of, so there is two different pathway, I think I already explained, or formation of a copper 3 species. From either of these intermediate or A or B, it will come to which one? Come to that okay. From there it will go to the corresponding enolate, and from there it will go to the, once you have a H3O plus, going to go to the corresponding product. So what is going to end up happening? I think this mechanism is already given in the lecture notes, so please go through that. You will end up going for a 1,4 addition. If you look into this cannot be the right. The answer B is correct, the neither C or D is the correct answer. Okay. So you get the corresponding the 1,4 addition product, and you will see in this throughout this lecture I am going to discuss this 1,4 addition again and again, and very similar mechanism, same mechanism going to happen in every single cases. So again there is a problem here, we using Grignard. As I mentioned, the Grignard is a so it's a harder nucleophile, so it is going to add to the corresponding the carbonyl group for via the 1,2 addition. So let's write the 1,2 addition product. What is going to happen here? So first thing there will be O minus, and then there will be a CH3 and a CH3. Of course, you can write O minus and magnesium Br plus or OMgBr. But then what is going to happen? This is not going to stop here. As you can see, there is a leaving group, a carbon chlorine bond is there. The O minus can go for a SN2 reaction to get rid of intramolecular SN2 reaction to generate the corresponding tetrahydrofuran. Okay. So if you see this cannot be the product, so that is not the product, this is also not the product, and the option D is the product. Okay, this is the correct answer. So here what is happening? The Grignard addition happening, and then there is the intramolecular cyclization. The major product formed in the following reaction. If you treat with Grignard, you have two different functional group in the starting. One is your ketone, another is ester. If you remember, which one is more reactive, then the ketone is more reactive than the ester, correct? So then the Grignard is going to add to the corresponding ketone, and if it is going to add, again you will end up forming this O minus magnesium Br plus, and you will have a CH3 here and a CH2 CH3 here. And then what you have? You have added only one equivalent, that is mentioned. Now in this stage, what is going to happen? You can see this is now ready for a intramolecular cyclization. It can react with the ester, okay, get rid of this group to go for intramolecular cyclization to form the so what is happening? You are forming a corresponding lactone. Okay. So now if you look into the answer, this is cannot be the answer because it is adding to the ester. This cannot be the only answer. It is going to stay like that. Again, not this one. So the option D is the the correct answer here. The major product formed in the following reaction is, what is happening? Again, in these reactions you are treating with isopropyl magnesium bromide at 25 degrees Celsius. So if you look into these compounds, you can see there is a carbon iodine bond there, and also you have a two nitro groups. Again, if you remember, we talk about isopropyl magnesium bromide. This is can use for a the metal halogen exchange. So that can allow the metal halogen exchange to generate the corresponding Grignard. And also if you remember, in this reaction, if you have electron withdrawing group with the aromatic ring, then the reaction rate will be much faster. And also most of the time you will see the carbon iodine bonds are used, and then some cases also you will see carbon bromine bond are used. But most of the time you will find the electron withdrawing groups are always attached in the ring that can allow this transmetallation reaction facile. So you will be generating this corresponding Grignard, which will be reacting with the corresponding allyl bromide to get to the allylated product. Again, as I mentioned, the advantage of this Grignard reagent is that this can form Grignard also by keeping this nitro group unreacted. So if you look into different examples here, this cannot be the different answer. This cannot be the correct answer. We can see here. So this option B going to be the correct answer, not C, neither the D. Okay. So I think I have already talked about this problem in the last class. Also, you have seen that this is a reagent used for a trans. So you can go for a metal halogen exchange to generate the corresponding, replace the iodine by corresponding, making corresponding Grignard. And then it can go for a in a reaction with a electrophile to get to the corresponding product. The major product formed in the following reaction is. So let's look into the problem here. You can see again we are talking about a reaction where you have a Grignard and a copper chloride. I think this type of problem comes several times in the exam, so that's why we are trying to give more problems in this area. So what is going to happen here? First thing, if you remember, once you treat with the ethyl magnesium chloride with copper chloride, you will be generating this diethyl cuprate. And that can be reacting with the this can be this can react with the alpha beta unsaturated carbonyl compound to introduce the corresponding. So you have a methyl group here, so you will be introducing another ethyl group. Now once you introduce it, you will be forming this type of corresponding carbon ion, so which can also come back and trap with the electrophile. So it is going to trap with the electrophile. Here it is a corresponding, you have a allylic bromide here. Okay. So it is going to react with the corresponding allylic bromide. You have seen that depending on the electrophile. So you can, in this particular stage, you can have a the electrophile can react with the oxygen or the carbon, that depend on the if electrophile is soft or hard, because this carbon is a soft center, so electrophile is soft, so that's why you can the reaction happening in the carbon center that can allow you to generate the corresponding product. So you will be generating the corresponding again you can see. So there are several different variations of this type of reaction where the different type of electrophile can be trapped in this position. So first one for addition, then it is trapping with the corresponding electrophile. Okay. So again this is the correct option here. The other options doesn't match with the product. The major product A and B in the following reaction sequencer. You can see there are several reagents given in this particular problem. Let's look into it. So here we are seeing organozinc. So this is a problem from organozinc reagent. We have a aldehyde here. Now if you treat if you treat with this particular reagent, there is a vinyl bromide and there is a alkyl halide. Once you treat with a zinc powder, as I mentioned, you will be forming corresponding zinc bromide. Okay. Now once you have this corresponding zinc bromide, and if you treat with a corresponding aldehyde, remember this can go for a Barbier reaction, and this will allow you to generate the corresponding O minus, or you can at the beginning it will attack here, generate O minus, correct, and then this can get protonated in the reaction medium to form the corresponding OH. So what is next? Once you get to this, now they are asking use TBDMS, chloride and pyridine. So what they are doing a protection of this corresponding alcohol. If you remember, we talked about the silicon protection. Again, TBDMS chloride, in presence of a base, it can able to convert to the corresponding and base. So it is the terbutyl dimethylsilane, correct? So that can introduce the terbutyl dimethyl group, dimethylsilyl group. Now if I try to write like that, you can clearly see there is a vinyl bromide and there is a styrene part here. So what they are going to do here? Now you have treated with palladium acetate, triphenylphosphine, K2CO3, CH3Cl. If you remember, if you have a olefin, like I think if you must have heard about this type of reaction, a styrene with a aryl bromide. Okay, palladium catalyst, which can forms the olefin. Okay, so this is a Heck coupling. Again, the mechanistically very similar to the Suzuki or the negative. So first there is a formation of oxidative addition, and then they go for insertion to the olefin. Okay, after the insertion, then there is a reductive elimination which goes to the product. So now here you have a olefin and then you have a vinyl bromide. Okay, so what is going to happen? This vinyl bromide go for oxidative addition. It is going to go for a insertion here. So that means and then let me try to draw some of the step here. Okay, so palladium will go for oxidative addition first to form a palladium 2, palladium bromide, then it will go for a insertion. Okay, once it will go for insertion, with the olefin, so it will be first there is a insertion and there is a reductive elimination. Once that will happen, you end up generating a product so you will be generating a exocyclic double bond here. You already have exocyclic double bond here and you have a OTBDMS. Okay. So you will be generating a product like this. So if you look into all the answer, we can see the first is option A. So this is the option A correct answer. Now let's look into that. I think this is the one looks correct. Okay, and then of course the one also in the C also, C and also in the D, they all looks the correct answer. Now if you go to the next answer, then we can find out that this cannot be the correct answer here, this cannot be the correct answer. Okay, so the only correct answer is going to be in the A, which is this one. So here the both A and B are the correct answer. So again, the option A is correct. So here you have several things happening: organoid zinc formation, Barbier reaction, protection of alcohol, then finally the Heck coupling. The major product A and B in the following reaction sequencer. Here you are treating this compound with a dimethyl cuprate. So let's try to draw this. Once you try to draw this, you will have an idea how this reaction is happening. So if you try to draw this in a half chair form, showing the epoxide is up, or if I can draw this in this way. Oh, I'm talking about, let's draw the other way. Not this one, we already draw this. Okay, so we already got the first, I think we already able to draw the half chairs. Okay, so if you draw the half chair conformation of this particular compound, now if you look into that, you are treating with this cuprate, correct, Me2Culi. Once you try to treat with the cuprate can able to approach. So if you see, this is the epoxide is up, so the nucleophile is going to approach from the bottom face here. So now if you have a methyl minus in the Me2Culi, the cuprate that can able to approach here and that can open the epoxide. Okay. If it is open the epoxide, you can able to draw them that this is, so this is forming in the above face, nucleophile is approaching from the bottom face, correct. That means this can give you a product like this, where you have a OH is up, or after it will form a O minus and then form a OH, correct, later, and you have a methyl here. So that is going to be your first product here. And then what is going to be your next product? Next thing, you are treating with the zinc copper couple and CH2I2. So if you treat with the zinc copper couple and CH2I2, and okay, there is a double bond also missing here, so we should also include that. There is a double bond here. So once you have a double bond and you are treating with the zinc copper couple, then this double bond is going to convert to the corresponding cyclopropane. Now the question comes, which phase the cyclopropane is going to form? Is going to be the above phase or the down phase? So we can able to answer this question very easily here, because once we have learned that once you have this OH group, this can act as a directing group here. So if you remember the tangent state for this, you always draw the tangent state like that, where okay, you can draw a tangent state and then you will have a zinc with iodine, so now you can see this can also form a chelation with the oxygen. Once it is forming a chelation with the zinc, the oxygen, the cyclopropanation is happening in the same phase of the oxygen. That is going to allow you to form the corresponding cyclopropane from the above phase, get to this cyclopropane. Okay. So that's why you will end up this as a final product. Now if you look into all the answer, first we have seen this is with the A. So of course the A seems right in this compound and this and this option. Then only the B seems right here. So option A is the correct answer because both A and B are correct. The major product formed in the following transformation is, again we are talking about a nucleophile addition, like 1,4 addition using the I think I already talked about this formation of the cuprate, and then it is going to come back and there is a allylation going to happen. I think a very similar problem we already talked about before, so I will not going to take longer time here. I think I can try to show you that once you show, I think the phenyl will be here and you will have a methyl, and then this is going to form a O minus, which is going to come back and going to take your react with the corresponding allylic chloride. So Cl, CH2, and this can attack here, get rid of Cl to get to a product like this. Okay. So again, if you look into all the options here, the 1, 2 or the 3, only the D option has this. Now we can also try to show you that the particular stereochemistry which they are trying to mention. For that we have to try to draw it first, so that we can able to explain it. So if you have this particular compound, we're having a carbon group here, and then you have a you have a phenyl group with the olefin. Okay, in the plane. So now there is a question comes that once you have a nucleophile, the nucleophile is going to approach from either of this phase or from this phase. Okay, again wherever it is going to approach, if it is going to approach, it is going to approach the opposite side of the phenyl, of course, just to because where the phenyl is going to, so that's two stereo going to be, so that means if phenyl is off, then it is going to approach from the bottom phase. Okay, the nucleophile come, and then there will be a minus. So if that is happening, let us try to draw it. So in this case, what is going to happen, we will have, and then we will have a single bond here, then a double bond here, O minus, and suppose you have a I think either way you attack so that the phenyl and the nucleophile will be in the opposite phase. So if the nucleophile is approaching, so if your phenyl is here, then your nucleophile approach from here. If you have a nucleophile is methyl, correct. And now once the allylation is happening, it will try to happen from this phase, just to avoid a steric. It is going to take a allyl from this side. Okay, it will take electrophile from this side. That can able to give you a stereochemistry like this. So of course the D is going to be the correct answer here, correct. So I think, as I mentioned, the others are even not close. The major product formed in the following reaction. Again, I think we have the several problems on this particular topic. You can see in the different time in the NET and GATE exams. So dimethyl cuprate is attacking here, and if you can clearly see, once you have some sort of a sterically bulky group here, that means so if you have a sterically bulky group here, like a isopropyl group here, then your nucleophile will be not approaching from this side because of the steric class. So the nucleophile will be approaching from the opposite phase. Okay. So that's why when the first attack is going to take place after the nucleophile attack, here your nucleophile is a methyl, like dimethyl cuprate. So this will end up generating. Let's draw the stereochemistry correct way. So you will have this methyl here, and then you will have a double bond here, O minus, and then you have corresponding isopropyl group. Now let's see what we have here. We also have one CH2 CH2 CH2I. Okay. So there are 4 carbons, so excuse me, I think this will be another carbon here. So we'll have a I here. Okay, I think sorry for the typo happening here, for some technical problem, but what is going to happen, it is going to go for intramolecular alkylation to get rid of this iodine, and that can end up forming a pyrocyclic compound. Okay. So this is going to be your correct answer. Now if you look into all the answer, these are not correct. The option D is the correct answer. The organoboron X, when reacted with diethyl zinc followed by reaction with para-iodotoluene in the presence of catalytic amount of palladium PPST whole 4 furnished a trisubstituted alkene. The intermediate and the product of the reaction respectively are. So they are asking that if you take this one and treat with diethyl zinc, what is going to happen? First thing they are asking this. I think I talk about the again a transmetallation reaction. When I was trying to talk about the synthesis of different type of reagent like organocopper, organozinc reagent, there is one of the other way how do you make the organozinc reagent. I think I talk about that you can take organolithium reagents and organogrignard, then take react with zinc chloride, that is one option. But at the same time I talk that if you have organoboron reagent, you use diethyl zinc, you can also convert to the corresponding organozinc reagent. So this is the example here. You have a trialkyl boron reagent, you treat with dialkyl zinc, you end up forming the corresponding zinc with ethyl. So you end up forming a corresponding organozinc, okay, by transmetallation. So once you get this one, now you are treating this with, what is the next question? They are saying you take with para-iodotoluene in the presence of palladium PPST whole 4. So you take this compound and this is a para-iodotoluene and you have this reagent here. Okay. You use palladium catalyst. What is going to happen? Which reaction you have remember? I think I already talked about this reaction. This is example of a Negishi coupling. Correct. So in case of palladium, what is going to happen? There is a oxidative addition going to happen with the aryl iodide. Then there is after that there is so this part the organozinc going to go for the corresponding transmetallation to introduce to get to the intermediate, where you will, let me just draw some of the intermediate for you. To generate this species where you will have a organozinc, that means you will have a palladium here with so this palladium 2 species is going to form, and from there they will have a reactive elimination. So that can end up you generating this product. Okay. So your option A is, so I think your first compound is this one and your second is this one. So let's look into all the option here. You can see the option A is showing, and then one of the important part you have to understand the stereochemistry. Here you can see these are the two ethyl group in the one side of the double bond, and the boron and hydrogen is another side. When it will go for the transmetallation, it will also keep the stereochemistry intact, and when it is go for a cross coupling with the palladium, it is also going to keep the zinc will be replaced by the aryl. So that means that we have to be very careful about that. Now if you see, this option cannot be right because it is saying one side ethyl, one side methyl. Again, this option also cannot be right because they are trans. They are also showing trans. Here you can clearly see that both are cis, and zinc and H is cis to each other. So this is the correct option, and also the polarity is also showing correct. So the option D is the correct option. Again, thank you so much for coming to the class. I hope you have learned some of the problems of the organocopper and the organozinc chemistry. Again, thank you so much for coming to the class. Thank you.